In this lesson, we're going to talk about mathematical models. No, not this type of mathematical model. We're going to look at linear mathematical models. We're going to cover how to determine if a linear model best fits a set of data, and we're going to find the equation of a line that best fits a set of data algebraically, as well as with a graphing calculator, using a feature called linear regression. Now here's a list of some of the new vocabulary in this lesson: mathematical model, finite differences, residual, least squares regression line, linear regression, correlation coefficient, and coefficient of determination. A mathematical model is based on collected data and can be used to represent how the real world works. A set of data may result in an equation or graph which can demonstrate a desired relationship or can be used to forecast future behavior. Once a set of data has been collected and plotted on a graph, it is then necessary to determine if a linear model can be used to best represent the data or if a nonlinear model should be used. You can tell the graph on the left is a linear model because it has a straight line going through its set of data points. A non-graphing approach to determining whether a line is a good model for a set of data points is using finite differences. Finite differences are simply the differences between each y entry in a set of data. If those successive differences are close to equal, then a line should be a good model for the data. So in this example, we'll use finite differences to determine whether a line would be a good model for this data. The estimated cash flows from a company over the 5-year period 1988 to 1992 are shown in this table. So we have our years and we have our cash flow. What we're going to do is we're going to determine whether a line would be a good model for this data using different methods. One, calculate the finite differences for the data points and then draw a scatter plot of the data. To find the finite differences, we just need to find the difference between each successive y entry. So here we see the years on the left, the cash flow in the middle, and on the right we're going to write our differences. Remember, the cash flow represents our y, so if we have 2.79 minus 2.38, we get 0.41. So our first difference is 0.41. 3.23 minus 2.79 is 0.44. 3.64 minus 3.23 is again 0.41. And 4.06 minus 3.64 is 0.42. Now, because the differences are approximately equal, a line is a good model for this data. To make a scatter plot of the data, we're just going to bring up our TI-84 graphing calculator, and we're going to go to our stat and make a new list. So we're going to go to Edit, Enter. Under List 1, we're going to enter in our x values, and here we're going to let 1988 correspond to the x value of 0. So we're going to have 0, 1, 2, 3, 4. List 2 is going to be our y values, so we have 2.38, 2.79, 3.23, 3.64, and 4.06. Now to look at our scatter plot, we're just going to hit second y equals, enter. We're going to turn this plot on, so hit enter again. Our x list is list 1, our y list is list 2. Hit graph, and there's your scatter plot. And you can see that a straight line would in fact go through that set of points. So one way to determine the equation of a line through a set of data points is to choose 2 of those points, and then simply find the equation of the line through those 2 points. Ideally, the same number of data points should lie above the line as lie below the line. However, for a large set of data, this method would most likely not result in the line of best fit. If we suppose that XR represents a data point, and XY represents a point on our line of best fit, this distance between XR and XY is called the residual, R minus Y. Residuals are a measure of error between the actual value of data, R, and the value of Y given by the model. They are the vertical distance from the line to each point. So this distance could be residual 1, this distance could be residual 2, this distance could be residual 3, and this distance could be residual 4. A positive residual is one that lies above the line, and a negative residual is one that lies below the line. If the sum of all the residuals is 0, then the line is probably a good fit, but if 2 different attempts end up with a sum of 0, then this still wouldn't indicate which line is the better fit. So if we had found two lines through a set of data points and we wanted to determine which line is a better fit, we could square each residual and then find the sum. The sum that is closer to 0 represents the better fit line. So in this problem, we'll create two different models based on this set of data, and then we'll use the residuals to determine which is a better fit. We'll call our two lines Model A and Model B. For Model A, we'll use the point 1, 2, and 3, 3. So Model A, we're using the point 1, 2, and 3, 3. For Model B, we're going to use the point 1, 2, and 6, 5. Now the equation of the line through these 2 points be y equals 1/2 x plus 1.5. And the equation of the line through these 2 points is y equals 3/5 x plus 1.4. So here's a graph of Model A, and here's a graph of Model B going through our set of data points. Now in this table, we have our set of data points on the left, and we have a set of points on our line right here. And the distance between our data point and the point on the line is called a residual. And notice there are 3 residuals that are negative. That means we have 3 points over here that are below the line, and we have 2 residuals that are positive, representing these residuals above the line. The sum of the residuals is 0, and when we square the residuals, the sum is 2. Now here is our table of residuals for Model B. And notice there are 4 residuals that are negative, representing these 4 points below the line, and there is 1 residual that is positive, representing this 1 point above the line, and then there are 2 residuals that are 0. The 2 residuals that are 0 represent the points that our line goes through. So the distance between the point and the line is 0. Now the sum of the squared residuals is 1.56. And because this sum is smaller than the sum in Model A, we know that Model B is the best fit through this set of data points. For any set of data, there is one and only one line for which the sum of the squares of the residuals is as small as possible. This line is called the least squares regression line, also called the squared error line. It is the line that minimizes the squared distance from the line to the points. The process used on a graphing calculator to find this line is called linear regression. So suppose I use the set of data points from the last example. In list 1 we'd have our x's, in list 2 we'd have our y. And we're going to use the linear regression feature of our calculator to find our equation of the line of best fit. So we're going to go to Stat, over to Calc, down to linear regression. And you can see that our x list is list 1, our y list is list 2. Let's go ahead and hit Enter. And here we have our slope, our y-intercept, and our r-squared and r value. The r value is called the correlation coefficient and is a statistical measure of how well the least squares regression line fits the data points. The r value is always between -1 and 1, and the closer this value is to 1, the better the fit. A perfect fit would be an absolute value of r equal to 1. So here you can see that when an r value equals 0, there's basically no relationship between the x and y variables. And as that r value gets larger, there's a stronger and stronger correlation between the x and y values. So this would be a strong positive correlation between the x and y variables, and this would be a strong negative correlation between the x and y variables. If we graphed a set of data and then used linear regression to find that the r value equaled 1, then that would mean there's a constant relationship between all x and y values, such as an equation y equals 3x plus 1, and the graph would look something like this. Now looking back at our example, the r value is 0.95, so there was a strong correlation between the x and y values. Now here's the r squared value, which is 0.92. Now r squared is obviously the square of the r value, and it's called the coefficient of determination. The book defines it as the proportions of variation in y that can be attributed to a linear relationship between x and y in the data. For a more detailed explanation of the coefficient of determination, please watch the video link below this one on my website. A circle can be circumscribed around any regular polygon. The lengths of the radii of the circumscribed circles around regular polygons, whose sides have lengths of 1 unit, are given as follows. So here we have a triangle where the side lengths are 1 unit long, the radius to the circumscribed circle would be 0.577. So square, pentagon, hexagon. We're going to draw a scatter plot, calculate the finite differences for the data points, find the model that best fits the data using the regression feature on the calculator, and then we're going to see what the correlation coefficient tells us about the data. To draw our scatter plot, we need to bring up our TI-84, turn it on, and we're going to go to Stat and enter in the number of sides into list 1. So we need to have 3, 4, 5, 6, 7, 8, and 9. List 2, we're going to enter in the radius for each circumscribed circle. So here are all our y values into list 2. To draw our scatter plot, we're going to go to Second, Stat Plot, hit enter, and we're going to turn it on and make sure that our X list is list 1, our Y list is list 2, and graph. Now this isn't the best view of our data, so we're going to go to Zoom, and we're going to go down to Zoom Stat, which is number 9, and that gives us a better view of the data. Now to calculate the finite differences for the data point, we're going to go back to Stat, we're going to go to Edit, and we're going to go over to List 3, and we're going to go up to List 3, and now we're going to say that List 3 is second list, go over to Ops, and we're going to say it's the change in list. Well, we want it to be the change in the Y value, so we're going to say the change in list of our second list 2. That tells us that it's the change in our Y values. Enter. So these are our finite differences, and notice they are all about equal. Now we're going to find the model that best fits the data using the regression feature. So now we're going to go to Stat, go over to Calc, down to Linear Regression, and we want to make sure that our X list is list 1, our Y list is list 2. We're not going to store our equation, so we can just hit Enter, Calculate. So here's our equation with a slope of 0.14, a y-intercept of 0.11, an r-squared value of 0.99, and an r value of 0.99. So here you can see that our correlation coefficient is almost 1, meaning there's a strong correlation between the number of sides and the radius of the circumscribed circle. So much so that you can say that the radius almost increases at a constant rate. While a linear model may in fact be the best fit, it's possible that a non-linear model may be a better fit. So one way to check if a linear model really is best is to construct a scatter plot of the residuals. That is, all the points x, r minus y. So if xr was a data point and xy was a point on our least squares regression line, then the scatter plot of the residuals would be all the points x, r minus y. Now if there's no pattern to the scatter plot, then the linear model probably was best. But if there is a pattern to the scatter plot of the residuals, then a non-linear model should have been used. So in this example, we're going to find the least squares regression line through a set of data, and then make a scatter plot of the residuals to determine if a linear model was in fact the best model to choose. So a local resident owns an espresso cart and has asked you to provide an analysis based on last summer's data. To simplify things, only data for Mondays is provided. The data includes the amount the workers were paid each day, that's salaries, the number of cups sold, the cost of materials, and the total revenue for the day. The owner also must spend $40 each operating day on rent for her location and payment toward a business loan. Sales tax have been removed from the data, so you need not consider them, and amounts have been rounded to the nearest dollar. So we're going to find a linear regression model for the daily revenue as a function of the number of cups sold, and then we're going to use a scatter plot of the residuals to determine if the linear model is a good fit for the revenue. Then we're going to find a linear regression model for the daily cost as a function of the number of cups sold. And then we're going to draw a scatter plot of those residuals to determine if the proposed model is a good fit for cost. And then finally we're going to find the break-even point where revenue is equal to cost. So we're first going to find a linear regression model for the total revenue as a function of the number of cups sold. So we'll enter in cups sold as our x values and our revenue as our y values into our list 1 and list 2. So we'll turn our calculator on, go to Stat, Edit, and then list 1 will enter in cups, list 2 will enter in revenue. Okay, so here's our information entered into list 1 and list 2. To get our linear regression, we're going to go to Stat, Calc, number 4 for linear regression. X list is list 1, Y list is list 2, and we're going to store our linear regression equation as our function 1, our y1 function. So we're going to go down to our store and we're going to say store this in our variables, y variables, one for function, one for y1, enter, calculate. Now here's your linear regression information. If you go to y equals, you see the equation. And if you want to see the graph of this linear regression, we'll go to zoom fit. Okay, there it is. Well, now we're going to make a scatter plot of the residuals to determine if the linear model is a good fit for revenue. So we're going to go to Stat once again, Edit. Now we're going to go over to List 3. We're going to go up to List 3, and we're going to assign List 3 to be the residuals. So we're going to hit Second List, go down to number 7 for residuals. So we're going to have a residual be assigned to List 3, hit Enter. Now here is all the residuals for our model. So now we want to make a scatter plot of the residuals. So we're going to go to Second Stat Plot, Enter. We first want to turn our stat plot on, and then we're going to go down to keep our X list as list 1, but our Y list is going to change to list 3. So we're going to hit Second List 3. Now before we graph our scatter plot, we're going to go to our function and turn off the equation. So we're going to go second quit Y equals, and we're going to go to this equal sign and hit Enter to turn it off. Now we're going to hit graph and find our scatter plot. Again, if you don't see it, just go down to zoom stat, which is number 9, and there it is. Now because there doesn't seem to be a pattern to this scatter plot of the residuals, that means the linear model is probably a pretty good fit. Alright, so now we need to find a linear regression model for the daily cost as a function of the number of cups sold. And daily cost consists of salaries, material, and the $40 it costs to keep the store open. So we're going to go to Stat, Enter. We don't need our residuals list anymore, so we can clear that. And what we're going to do is we're going to enter in salaries, material cost, and then in list 5, we'll create the sum of salaries, material costs, and the $40. So in list 3, we'll enter salaries. Okay, in list 4, we're going to put the material costs. Now in list 5, we're going to write an equation, and we're going to go up to list 5, and down below, so go up to list 5, hit enter, and we're going to say that list 5 is equal to list 3 plus list 4 plus that $40 per day. So the daily cost, salaries, materials, and the $40 per day. Enter. So you can see list 5 now represents the daily cost for operating the espresso stand. So now we're going to find the least squares regression line by going to Stat, Linear Regression. And this time, instead of having our Y list be list 2, our Y list is going to be list 5. So second list 5. And we're also going to store our equation as equation 2. So variables, Y variables, function, this time Y2, enter, calculate. Okay, so here's our linear regression information. If you go to Y equals, you'll see our new equation. Now from here, if you want to see the graph of both equations, remember we have to turn equation number 1 back on, and then we're going to go to zoom, zoom fit, and there we can see the graph of both equations. Next, we're going to find the scatter plot of the residuals for cost. So we'll go to Stat, we're going to go to Edit, and this time we're going to go to list 6, and we're going to call list 6 our residuals list. So we're going to go to second Stat, down to number 7, enter. Now list 6 is now the residuals for the daily cost. So now to enter this scatter plot, we're going to go to second Y equals. We're going to turn on our scatter plot, and again this time we're going to use our Y list as L6. And before we can go to our scatter plot, we need to turn off our equation. So go to Y equals, and on each equal sign hit enter. And now we can go to graph, and again if you don't see it, because we're going to be graphing our lists, we go to zoom stat, which is number 9. Now here is a scatter plot of our residuals of the daily cost. And again, because there's no pattern to our residual scatter plot, that means a linear model was the best fit for our data. Finally, we're going to find the break-even point when revenue is equal to cost. Well, we have our revenue equation as equation 1, and we have our cost equation as equation 2. So we're going to turn those back on. We're going to go to Zoom Fit. And at the point where the cost line is equal to the revenue line, that's the break-even point. So in order to find that break-even point, we're going to use the intersection feature of our calculator, which is second trace down to number 5 for intersect. Now, right now it's saying pick a point on curve 1 that's close to the intersection point. So we'll just move a little closer, hit enter. It moves the cursor over to the second curve. We'll hit enter. Then it says guess. So I'll say that intersection point is about there, enter. And right there it says our intersection point occurs when x is about 89.6. Since 89.6 cups cannot be sold, 90 cups a day must be sold to break even. Alright, for this example we're going to use the linear regression feature of our calculator to find the line of best fit through this data. And then we're going to use that line of best fit to make a prediction, and then we'll determine if the line was the best model for the data. So here it says the total number of farm workers in millions in selected years is shown in the following table. So we have the years 1900 through 1994. We're going to use a linear regression to find the equation that models this data. So you need to bring up your calculator, turn it on, and we're going to let x equals 0 to correspond to the year 1900. So we're going to go to Stat, Edit, and we're going to enter in all our x values in list 1, and I'll do that now. Okay, now we need to enter in the number of workers in millions into our list 2. Okay, now that we have our information into list 1 and list 2, we're going to go to Stat, over to Calc, number 4 for linear regression. My calculator is already set to use the X list as list 1, the Y list is list 2. We want to store this equation into our Y1 function, so we're going to hit the variable key, go over to Y variables, function, Y1, and calculate. Okay, now that we know our equation, the second question says, when will the number of workers be 150 million? So we could just go to our table, second table, and you could scroll down until the Y value is 150. So here you can see 130 years after our initial value or initial year of 1900 will be about 150 million workers. So that's in the year approximately 2030. Now we just need to determine if the line is the best model for the data. And to do that, we're going to graph a scatter plot of the residuals. So we're going to go back to Stat, enter, we're going to go over to list 3, and again we're going to assign list 3 to be our residuals. So second list, go down to residuals, enter, enter again. Now we've got a residuals list here, and now we just need to make a scatter plot. And remember, before we do our scatter plot, we need to turn off our equation. So we just need to go to this equal sign, hit enter. Now we're going to go to second stat plot, enter, turn this stat plot on, make our Y list list 3, so second 3, and graph. If you don't see your data, we just need to go to zoom 9 for a zoom stat plot. And there it is. Now because there seems to be a pattern to the scatter plot of the residuals, that means a nonlinear model probably should have been used.